So we're going to move on to Bill Schmidt. And Bill's going to give us an update on some experimental drugs he's been working on.
Thank you, Ed, and thank you, Dan, especially for this chance to talk longer than I had thought because Marie's not here.
Wait a minute, we didn't give you any extra time.
Doesn't work that way.
And as I say, now we're going to do something very different. We're going to talk about some new pharmacology, some new science that you probably have not heard about before. But let me put this in context. 3 years ago, I got a call. I work as a consultant, as you can see now, and I work with academic labs and with pharmaceutical companies, small companies, large companies all around the world, by choice, in the area of pain medicine. After working with big pharma for several years and then with smaller biotech companies, I decided that what I really wanted to do was to become a consultant to be able to help a broader range of companies. So 3 years ago, I got a call in my office, and a person with a very thick Eastern European accent said, "Hello, is this Dr. Schmidt?" And I said, "Yes." And he said, "Do you know anything about pain medicine?" And I really had to chuckle because this is where I spent my entire professional career, by choice. And so I said, "Where are you calling from?" And I honestly expected that he was going to be calling from Romania. But he said, "I'm calling you from the University of California, Davis." Now, as you can see, my office is in Davis, and he was less than 2 miles away, and he had no idea where I was. He was simply looking for somebody who could help to transition the product from an academic environment into real clinical development. And so I said, "Come on over to my office, we'll meet in half an hour." And what I heard was so profoundly exciting to me that I said to a team of several people coming over from the university that this is so exciting, I will work for you free of charge until we get this project financed. So that's the story that I'm going to tell you. What I heard that day is a lot of what you're going to hear right now, and we are now moving this toward initial clinical trials that will start next year. So as a conflict of interest, I do work with a lot of different companies, and so I may be completely conflicted or not conflicted at all because it would be spread too broadly. But in this case, data are not trade secrets, and anything I talk about is entirely my own opinion. The company that was started after this conversation that I had is called Epoxyeicosatrienoic. This was spun out of the University of California, Davis, 3 years ago, and we're working on a new class of drugs called soluble epoxide hydrolase inhibitors as a therapeutic target for pain. Now, I've never heard of soluble epoxide hydrolase. It's an enzyme. It's an enzyme that's in the same pathway as the prostaglandins and the leukotrienes. So if you start at the top with arachidonic acid, it can be metabolized into pro-inflammatory and pain-inducing substances such as the prostaglandins. It can be metabolized into leukotrienes, but a third part of the pathway that honestly I had never heard of until 3 years ago was a profoundly anti-inflammatory analgesic pathway that derives very short-acting fatty acids called EETs, or Epoxyeicosatrienoic acids. These are intracellular analgesic anti-inflammatory substances that normally then would be broken down by the enzyme SEH, soluble epoxide hydrolase, to dihydro compounds that are less active. But what you can do with an inhibitor is to block the enzyme and substantially increase the level of EETs that you can measure both intracellularly and as a biomarker in the blood. So it turns out that this call that I had gotten was not from the head of the department, but rather from somebody working for a senior professor at the university who was not in the medical school, as I might have anticipated, but in the entomology department. He was a bug doctor. And going back to the early 1980s, he was trying to figure out how do butterflies get formed from caterpillars? What is the key regulatory step to allow caterpillars to transform into butterflies? And it turns out the same enzyme, soluble epoxide hydrolase, is responsible for that step. If you block soluble epoxide hydrolase, you prevent caterpillars from going into butterflies. Now, if you're trying to treat certain types of insects and prevent them from metamorphosizing, that maybe makes sense. But then he began to ask what other cells have these, and he found them in potatoes and tomatoes, and later on in mice and rats, and in human cells. And then starting some years ago, he developed inhibitors of the enzyme. APAU is one of the early inhibitors that he developed, and then systemically In his lab, they synthesized over 3,000 inhibitors and moved the potency more than 2,500-fold from the early compounds, EPAU, down to compounds that are so potent they're not even shown at the left-hand side of the field here. We now have compounds that are going into human clinical development that are 50 picomolar inhibitors of the enzyme. So we will be talking therapeutically about sub-milligram doses for humans. One of the lead compounds is EC1728. This is one we're not developing for humans, but rather developing it for animal medicine. And its function would be to increase intracellular levels of EETs, usually by 4 to 8-fold, but also to stabilize those and to make the EETs stay around instead of seconds as they do under a normal circumstance, to stay around for hours or even longer. So the compounds that we are working with are long enough lasting that they would be given only once a day for treating either acute or for chronic pain. The target is intracellular. These are sections of brain, superior cervical ganglion and dorsal root ganglia, where the red markers are pan-neuronal markers. The green marker shows the evidence that these cells have soluble epoxide hydrolase, not only in their nucleus, but as it projects out into receptor fields. The compounds have been tested now in a wide variety of pain states, both acute pain and chronic pain, inflammatory pain, neuropathic pain, late stage and early stages of arthritic pain, and in every one of these instances they have profound analgesic and anti-inflammatory activity. In combination with traditional analgesics such as NSAIDs, they synergize the activity of NSAIDs, but more excitingly, they also block GI erosions. And if you have animals with existing GI erosions, they promote healing from the GI erosions, even if you continue taking NSAIDs at the same time. It almost sounds like magic, but this stuff actually really does work. It's a totally non-opioid profile. There are studies that have been done for self-administration or for liking scores, and I'll show you some of those. And there's no addiction liability that's been shown in rodent tests. The lead compound that we've chosen for clinical development is actually a peripherally restricted compound. Keep it out of the brain, although it does work in the central nervous system. We potentially would be able to avoid a lot of the cognitive or other CNS side effects that we have with drugs that are used to treat acute and chronic pain conditions. Now, because we're talking about acute pain, which often involves inflammatory pain, let's go to the right-hand side of the slide here first. This is an experimental model of inflammatory pain using LPS, or lipopolysaccharide, to induce an inflammation in a rodent model. And if you start out with 100 as being the baseline sensitivity of animals to von Freyhairs that are used to probe for reaction, it goes from 100 in the baseline condition to, if you follow down at 0 where the lipopolysaccharide is then administered, you see that there's a hyperalgesic state that exists. And if you then administer celecoxib prior to giving this the LPS stimulus, or if you administer APAU, thank you. Now I've got a pointer. You can see that celecoxib will have an anti-inflammatory and analgesic action compared to the placebo situation. But APAU administered at the same time in different animals as celecoxib actually prevents the inflammation from occurring. And it then continues to have a profoundly more effective anti-hyperalgesic and anti-inflammatory effect than celecoxib. Over here in neuropathic pain, where it's a diabetic neuropathy model, celecoxib and other NSAIDs are not known to be particularly effective in treating neuropathic pain, and this is shown here. But APAU administered subcutaneously has a very significant anti-hyperalgesic effect that appears to last, in this case, for about 6 hours. With more potent, longer-lasting compounds, we have even longer duration of action. How about indirect comparison with morphine? Here again is a lipopolysaccharide or LPS model of inflammation. If we have here the control latency for probing with von Freyhairs, you see that with LPS inflammation, the animals become hyperalgesic, so they have a faster response time. If you administer morphine, shown in blue, you have an anti-hyperalgesic or analgesic action that lasts, in this case, for maybe an hour, and then the morphine at 1 milligram per kilogram falls off. But the experimental compound TPAU in a dose-response fashion has a more prolonged and more effective analgesic or anti-hyperalgesic action than morphine. Administered locally or by interplantar injection, the same compound, TPAU, also has profound analgesic activity. This is actually not TPAU, it's a different soluble epoxide hydrolase inhibitor that has a local anti-inflammatory analgesic action that is at least equivalent to locally administered morphine. But take a look at the difference in doses. For morphine to get this level of analgesic effect, you have to go to 10,000 nanograms administered interplantarily, where the epoxide hydrolase inhibitor is effective at 10 nanograms. So it's over 1,000 times more potent administered locally than morphine. Because I know we have a lot of anesthesiologists in the room, I assure you that compounds work if you administer them intraspinally. This is a different model compound, AEPU. And by the way, the reason I can show some of these compounds is that a lot of this work has been published. As an academic lab, before they came to me, they had to publish all of their work. And so the structure of the compounds that were used for these studies are actually shown in their articles. The ones that we've chosen for human clinical development are more proprietary, but they work the same way, and they're much more potent than what you see here. This is a model of carrageenan-induced inflammatory pain with AEPU administered by an intraspinal route of administration. And you can see here, with an administration of 3 micrograms given intraspinally, it has a profound effect against mechanical withdrawal threshold pain and thermal withdrawal threshold pain compared to the control situation. Now, one of the things that we've been careful to do in describing the action of this compound is to use the term anti-hyperalgesic, which you heard with one of the earlier presentations that I think Esther talked about, as opposed to analgesic. And that's because these compounds are not primary analgesic substances. In fact, they have no analgesic activity if you inject them in naive animals. Well, think about that. You have a compound that is inactive in naive animals, but does produce a reduction in pain responses, in the interpretation of pain, in animals with a pain condition. Why would that occur? Because these compounds as enzyme inhibitors are only effective when they can increase EETs, and EETs are increased by the initiation of trauma. So if you have no trauma, you don't have any increase in EETs, so the compounds would not be active. This is actually shown here, where in naive animals, where the compound is administered subcutaneously, you can also do it orally. And here we have APAU. The compound at 100 milligrams per kilogram has no activity at all in terms of increasing pain thresholds, but morphine at 3 milligrams per kilogram shows the typical analgesic activity that you would expect morphine to have in naive animals. The compounds are effective, in fact, more effective than pregabalin and gabapentin in treating neuropathic pain. This is a model of diabetic neuropathic pain in streptozotocin treated rats. And in this case, the animals starting out here at baseline, they're administered streptozotocin, their analgesic or their baseline response to von Freiherr drops because they're in a hyperalgesic state. And that hyperalgesia lasts for the 6 hours that are shown on here. In fact, it lasts a lot longer than that. If you administer pregabalin, there is a reduction in the hyperalgesia, so you turn the animals more toward a less pain state, but then its effects wear off over a period of about 6 hours. The soluble epoxide hydrolase inhibitor, and in this case it is actually our lead compound to go into humans, is more potent and has a larger and more prolonged anti-hyperalgesic effect, returning animals to a totally normal pain sensation than the animals treated with pregabalin. If you go to higher doses of pregabalin, by the way, the animals become essentially comatose. They lose their righting reflex. And so in this case, there was no loss of righting reflex, no cognitive deficits or other motor deficits that were exhibited. And the compound is much more potent than pregabalin and more effective in this model. Now, the reason that I got so excited about this product was not because of the studies that they've done in mice and rats. I see thousands of studies with mice and rats, and companies that have exciting new products to develop. I get more interested when I see animal models of naturally occurring pain. This is a model in naturally occurring osteoarthritis in aged dogs. There were 30 animals. They're at a facility in Canada that specializes in doing studies in aged animals with osteoarthritis. And in this case, this is the compound that is now being evaluated for development as an analgesic compound. It's EC1728, given at 5 milligrams per kilogram. The compound has progressive decreases in pain scores as the compound is administered once a day for 5 days. It needs to actually go much longer. My experience in doing human clinical medicine is that if you want to test a compound for anti-arthritic activity, you will probably find maximal effects after you dose for 2 or 3 weeks. But to see that this had onset in a day or two and had a significant analgesic effect in these animals was really quite important. But then there was a story in horses with neuropathic pain that really caused me to become excited. This is a horse that was at the UC Davis Veterinary School, one of the larger veterinary schools in the United States. The horse has a condition called equine laminitis, or founder's disease. It's a profound inflammation of the forehoofs that becomes neuropathic over a period of time as the tissue becomes toxic. This animal had been on her side for 2 days prior to intervention with an experimental soluble epoxide hydrolase inhibitor. And in fact, the animal had been scheduled for euthanasia. Horses don't do very well when they're on their side for 2 or 3 days. They will die on their own because they have respiratory failure. There was Animal Care and Use Committee approval for an experimental treatment under this condition, and actually the guy with the pistol who was going to euthanize the horse was standing nearby just in case something went awry. So 1 dose of the compound was administered intravenously, and in 3 hours, the animal was back up on her hooves. Within a few hours after that, she was eating again. They gave doses for 5 days, once a day for 5 days, and then ran out of drug and stood back and said, what's going to happen? And what happened was that the animal had complete resolution of symptoms and is still alive today, being used at the university to train students how to ride horses. This is actually a thoroughbred horse. This is a direct descendant, the granddaughter of Seattle Soluble, who was a Triple Crown winner and was put down due to equine laminitis. This was when I said, I'll work for you free of charge. Since then, 10 more, should have been on here, a total of 10 more horses have been treated, and 8 of the 10 horses had favorable outcomes with the soluble epoxide hydrolase inhibitor. Pain in horses is measured much the same as it is in humans on a 0 to 10 scale. Here is the pain scores for this horse, becoming progressively smaller over a period of time. Morbid hypertension also disappeared over a period of 2 or 3 days. And here's the horse after a week when we ran out of drug, walking around the paddock as though nothing had happened. And here it is, replicate studies, and these are published. 8 out of 10 horses responded favorably to treatment with EC1728. In the condition-place preference test, the compound had no likings in the absence of pain. So unlike morphine, which has a liking score that shows that it has abuse liability, the epoxide hydrolase inhibitor did not. But in a condition with diabetic neuropathy, then the animal does have a preference. The animals like the compound when it's been used because they have a pain situation. The fortunate part of the story is that, well, actually the unfortunate part of the story is, with a novel compound that's this novel, we could not finance it with venture capital or with angel investment because it was so novel that people just really didn't understand the pharmacology behind it. But what was very fortunate is that this qualified for the first ever clinical stage grant from the NIH Neurotherapeutics group that will provide full funding for all activities through phase 1 clinical trials. This became effective in January this year. So it's a spin-off from the University of California in December 2013. NIH funding supported the early stages of development and now later stages, and we will be moving forward into clinical trials in humans next year and also in trials with animals. Thank you.
Hi, I'm Jane from Oxford. That was really interesting. How specific is it for that enzyme, and how nervous are you going to clinical trials based on the France clinical trial with the FAAH? inhibitor?
So we did a spectrum screen, which is provided by Nova. We used to call the Nova screen. Eurofins is actually the company that runs this now. With more than 100 enzymes, receptors, ion channels, it was highly, highly selective for the enzyme soluble epoxide hydrolase. Okay?
Great, thank you.